All right, so now we are going to look at the FOM cycle. Now, the good thing about FOM and GMRES is that the code is almost exactly the same for both methods. We're just gonna once we run the Arnoldi algorithm to get our basis for the Krylov space, there's just different systems that we solve. But otherwise, it's very similar. Otherwise, what I mean is, aside from the fact that we solve a different system, the code is exactly the same. In fact, we're just going to copy and paste it once we do it. So here is the function signature FOM cycle. The reason it's called cycle is because this could be embedded inside of a bunch of different what's called restarts. So you run this for a certain value of m, then you take your guess, and that's going to be your new guess for the next cycle. But we're just going to do one cycle here. Okay, so A is the matrix, B is the right-hand side in AX equals B. This is the size of the Krylov space to build. This is the X naught. So if you're doing a cycle method, if you're doing several cycles, you need the user to be able to pass in the next X naught to compute the next cycle, or maybe the user just already has a good guess at a vector. And here is the tolerance right here. Tolerance is 1e minus 10. That's basically just what we're going to pass to the Arnoldi algorithm at this point. We'll modify this in a little bit, and we'll have that'll come into play in a different way as well. It's going to return x and the norm of the final residue. This is actually not quite right. It's going to sort of return the relative norm of the final residue, but we'll talk about that when we get there. There's many different ways that you can design this function. I designed it this way, and one way to think that might be a reasonable choice is that this is how SciPy has. SciPy doesn't have an FOM function, but it has a GMRES function, and this is how it. This is basically how it implements, or this is the function signature in essence for the GMRES method. Okay, so first of all, we need an X naught. So if the user has not provided an X naught, we will provide one. If the user cannot afford an X naught, one will be provided. Sorry, that's a dumb joke. Okay, so now we're going to say X naught. So in the book, the author of the book, I don't know why, I'm sure he has good reasons for this because he's obviously an expert in this and I'm not. He does a random vector for the first vector, for the initial vector here. I don't know why. Maybe there's good reasons. Maybe you guys can tell me what the good reasons are for that. But I'm just going to look at the zero vectors. And again, it needs to match the columns of A because we're going to be doing A times X naught. So even though A is square, conceptually it's equal to the number of columns. So that's why I have the shape as, that's why I have A dot shape 1 instead of A dot shape 0 or something else. Okay, so now I need to make my zero vectors, or my V and H matrices. So V is going to be equal to NP dot zeros. And again, the size, the number of rows in this needs to equal the number of columns of A. So we're going to do A dot shape 1. And then there's going to be M plus 1 rows. Okay, now the next thing we need to do is our H matrix. So H bar is going to be equal to NP dot zeros. And again, there's going to be, or not again, but there are M plus 1 columns and M rows. I like to put spaces when I can and when it makes sense. Okay, so now we're going to compute the first residual. R naught is going to be equal to B minus A times X naught. I do not understand why. You know what? I'm just not tabbing properly. I think what happened is I made this, but see, that's not. Why is it doing like that? There we go. I wrote this in Google Colab and downloaded it and opened it in Jupyter. So I think the tabs are a little bit different. Indulge me for a moment while I tab these over. Okay, these all look right. Okay. All right. Okay, here we go. All right, there we go. That is our first residual. Now we're going to need the norm of this residual. So I'm going to say R0 norm is going to be equal to np dot linalg dot norm r naught. Now there's different norms that we could use. We could use the Euclidean norm, which is what we're using here, the infinity norm, things like that. I am going to consistently be using the Euclidean norm here. For a number of reasons. In terms of orthogonality, that's just sort of the thing that makes the most sense to me. Now, at the end of it, well, anyways, so that's why I'm using the Euclidean norm. When we test it, we'll also look at the max norm between the actual solution and the solution that this gets, but we'll forget about that for now. And we're also going to need to know the norm of B. Now, the reason that I'm saving these as variables is because we're going to use them several times. I'm saving these as variables because we're going to need to use them several times, and I don't want to compute them several times. Okay, so the first thing is, well, what if R naught is equal to 0? If R naught is equal to 0, then that means X naught is equal to the answer. So we're done. Now, so I need to have something like this. If R naught norm equals 0, then what we're going to do is we're going to return X naught, and the norm of the final residual, what we're going to return is not like, this is the norm of the final residual. What we're really going to do is return the relative norm of the final residual, so divided by B norm. Because again, for the similar reasons that we have in the Arnoldi step, we have where is it? Right here, right? We're not just texting to see if H next is less than or equal to a certain number. We want to see if it's less than or equal to a certain number relative to AV norm. Same idea here. Okay, so that's what we're going to have. But now what this tells us here is R naught norm. Our test should not be if R naught norm is absolutely less than or equal to a certain value. It should be if R naught is less than or equal to the tolerance times B norm. Okay, so that's what we have here. So that's why we're going to do it this way. Okay, so now we're sort of out of the way. This sort of gets us past the initial setup. We have our guess. We've handled the case of what happens if we just magically guess and X naught happens to be the solution. We're good there. So now we can get into the actual, like, the loop part of FOM. So we're gonna have a variable called breakdown. This is not something that gets returned, but it's something that we're gonna need to monitor. Okay, so breakdown is gonna be equal to false, and we're gonna set our integer j equals 0. J is gonna count up to m. So while j is, so this is gonna be very similar to when we tested the Arnoldi method up above. If we want to have an n by m plus 1 matrix for V and an m plus 1 by m matrix, we need to, and the way we have coded our Arnoldi loop, j needs to go up to m, but not m plus 1. Okay, so this is how we're going to do it. So while j is less than m plus 1, and we have not broken down, okay, so we're going to say L and breakdown is equal to the Arnoldi step. Okay, remember L, the Arnoldi step returns a number that says how many usable vectors we have and whether or not we have broken down. Okay, so we're going to break down Arnoldi step A, V, H bar, J. The tolerance is going to be equal to the tolerance that was passed here, and that is going to be it. Okay, and then after every one, we're going to do J plus equals 1. Okay, so this loop can terminate based on two conditions. Either J is equal to m plus 1, or we've broken down. If J is equal to m plus 1, then we're going to have, so in other words, if we finish it, our matrix V is going to have m plus 1 columns, but we only really care about the first m columns. our matrix H bar is going to have m columns, and we care about all of those columns. That's if we make it through the all of the Arnoldi steps and we never have breakdown. Now, if we break down L, okay, that tells us how many usable vectors we have. So if we break down, what we're going to have is the first L vectors of V are what we want to use, but also the first L columns of V are what we want to use, but also we want to use the first L columns of H. So what we're going to do here is say K is going to be equal to the min of L and M, and then okay, we're going to remember that based on the theory, the problem that we're going to solve is H bar equals beta times E1. Sorry, H bar Y equals beta times E1, where H Y is equal to beta times E1, where beta is the norm of R naught, and E1 is just a vector with a 1 in the first position and 0 everywhere else. Okay, so I'm going to say BE1 is equal to NP dot zeros K. Whoops. And now I'm going to say BE1, the first entry, is going to be equal to R naught norm, like this. Okay. And now we're going to say Y is equal to SP dot linalg dot solve H bar up to K, whoops, and then we're going to solve it for BE1. Now, notice that H has some very nice structure. It's a Hessenberg matrix, and we are not taking advantage of that here. Okay, so this is something that you can fix, and I think for the project, for the final project, I make you fix it. Maybe not for FOM, but for the GMRES, you have to multiply it by Gibbons rotations. But anyways, for now we're just going to do it like this. It's typically okay because this is a much smaller system than what we're actually solving. But this can also become prohibitively bad, prohibitively big. Okay, and now we're going to say the solution is equal to x naught plus V all the way up to K again. If we stop, if we stop, well, anyways, this is what we need. All right. Let me just make sure I've done everything here correctly. Oh, times Y. All right. Yeah. So just to recap, if we've done everything correctly, V has M plus 1 columns. The last column, the index, is equal to M. So we need to go up to the M minus 1 index column. So if we go through everything, K is going to be, that is, if we don't break down, K is going to be equal to M. So that's going to be an M, which means we're going to go up to the M minus 1th index column, which is exactly what we want. On the other hand, if K is equal to L, that is, we break down. If we break down, then the first L columns, the first L columns are going to be useful. So that means the columns 0 through index L minus 1 are going to be useful, and this is exactly what we want to have there. Okay, so then what are we going to return? Well, we're going to return the solution, and we're also going to return the relative residual. So NP dot linalg dot norm B minus A times the solution, and we're going to divide by B norm. Okay, so I'm going to run this. Okay. Unindent does not. What? Oh, none. That's probably not what I need to have there. Oh my gosh. What? Oh, oops, hold on. There we go. Okay. All right, so this, I think everything is coded here correctly. We will do the GMRES after we make sure we have this correct. So this right here is not, this is not in your project. So what I've done here is I've just copied my code for my SOR method. This is sort of the non-optimized SOR method, and this is like the super optimized in some sense. I mean, as much as I am going to be willing to do right now, optimized SOR method, just for comparison purposes. Okay, to see, you know, which one, just to compare the methods. I think that's a natural thing to do. Anyways, so now what I want to do is I want to I need to set up sort of a testing thing here. So in, just like it has in the book, I'm going to start with in is equal to 32, and a is going to be equal to build operator. Okay, and in, okay, remember that first thing is the number of unknowns in each direction, and this is the function build operator is like making a Poisson matrix in 2 dimensions. So it's going to be a 32 squared by 32 squared matrix, and then I'm just going to use the functions that were defined above. So a coefficient, b coefficient, d coefficient, e coefficient. Let me just run this. Okay, yep. See. Okay, there we go. The only reason I ran that is just to see if there's typos. And you know what? No surprise, there were typos. All right, so that's what I'm going to have. That is the matrix that is set up. Now I'm going to make a true vector. This is going to be the solution. It's just going to be in p dot ones. We could also make this a random vector if we wanted to. A dot shape 1. Again, we're going to be multiplying it by a, so the number of entries in x true needs to be the number of columns in a. And then b is going to be equal to a at x true. Whoops. Okay, and the idea is that we're going to solve the system with b. We're going to get an x, and we're going to see how this compares to the actual solution. Okay, and that's exactly what we're going to do now. We're going to do xmr. I'm going to say xm is the solution, is going to be equal to FOM cycle. A, B, I'm going to leave it, I'll do m is equal to 10 for now. M is equal to 10. I think that's all I need to give it. A, B, M. I'm gonna have it compute its own x naught. Okay, I'm just gonna run this just to make sure everything works. Okay, it does it because why? It says B norm isn't defined. B rom, of course. How many of y'all caught that? Okay. Oh, I never, in the Arnoldi step, I never told it what R naught is. Okay, so Arnoldi, the R naught algorithm, R naught argument is after the J. Okay. Okay. Wow. Mm-hmm. All right. Okay, cannot unpack. It always seems to happen this way, doesn't it? Oh, wow. Um, there we go. Holy moly, here's a problem. Return none. Whoops, I didn't change that part. And it didn't show up down here because it didn't show up here in the test because I'm not setting it equal to anything. Yes, okay. Yes, okay. So j plus 1 and then false. Okay, there we go. All right, I'm glad you guys got to watch me do that. So let's see. Okay, perfect. Now I'm going to I want to print out, how fast, how close did we get to the right solution. Now, in this first case, because we only did m up to 10, I think is going to be a pretty big difference. So print f. Okay, so this is for the FOM method. I'm going to call it error. That is the difference between the actual solution and what we computed. So np dot max np dot abs, and we're going to do x true minus xm. Okay, and I'm going to say relative residue, or sorry, not residue, relative residual. That's going to be the r is equal to r. I think that's what I want to do for now. Okay, so we can see here that the error is pretty big. I mean, we started with a vector of all ones, and the maximum difference is 1. So this really has not done anything. Now, if I make this go up to 100, let's see what we can get here. Okay, so now we have something a little bit better. Okay, what about 150? Something that's not as good. 200. Okay. 500. Okay, so when we do it 500 times, okay, we get an error between the actual answer and our estimate of 10 on the order of 10 to the minus 8. And this is the relative residual. In general, the relative residual is going to be bigger, the relative residual is going to be smaller than the error, and the smallness is going to be based on properties of the matrix. Okay, we've done these computations before, because the residual, the norm of the residual, well, the residual is b minus ax, but what is b equal to? B is just equal to ax true. And this is going to be less than or equal to the norm of a times the norm of x true minus x. And this is equal to the norm of a times the norm of the error. Okay, now we're measuring, this is the infinity norm of the error, and this is the L2 norm. But since actually what we're doing is we're dividing this by the norm of b, that normalization should take care of some of that discrepancy. So we're going to have this like that. And so now what we measure, like we have the relative residual right here. It is going to be less than or equal to the norm of a times this, we can sort of think about this as maybe being some approximation to the infinity norm of the error. Okay, so the relative norm is going to be less than or equal to the norm of a, which is going to be bigger than 1, times this. And so, and again, what it tells us is that the norm, the residual should be smaller than the absolute error, which is exactly what we see here. Okay, so in terms of picking out what we want, our tolerance to be, If we want to, in just a moment, we'll see what happens if we sort of run this method until we reach a desired tolerance. We're going to have to keep things like that in mind. So I actually think we can do this in many fewer attempts. Like this. Well, 3,500 is way too long, not what I meant. 350. Okay, doesn't really matter, but I'm going to keep going here. Okay, anyways, so this works. This shows that our method works. One thing that I do want to do is see how long it takes. So tick equals time dot time, and down here, talk equals time dot time. Oh, got this on the wrong thing here. I do not care how long it takes me to print that. Okay. All right. And time equals talk minus tick. Okay. So time 0.05 seconds. All right. Now, just for comparison, let's look at this same thing, but for SOR. If I do SOR, we're gonna need, so let's say my SOR, we're gonna have A, we're gonna have B, we're gonna have W. Do I have to give it tolerance? Yeah, we're gonna give it W. I'm gonna say W is equal to 1.9. And then here, tolerance is equal to 1E, let's do -8. Okay, so, and then what we're gonna have here is SOR. Notice that the SOR method actually turns the residual. It returns the residual and not the norm of the residual. So I'm gonna do, and definitely not the relative norm of the residual. So here I'm gonna do np dot linalg dot norm r divided by np dot linalg dot norm p. Okay, now what's going to be the problem with this code? Oh, max iters equals, I'm going to do 5,000. That's way too many. I think it should. Oh, there's 3. Okay. Oh, there's also the number of iterations. So let me put this. And iters equals n. Okay. Ah, dang it. Okay. Whatever. Okay, so SOR took a little bit longer, but notice it took maybe okay, if we compare these methods. Oh wait, it only wow, okay. I am a little bit surprised by that. We're also getting much closer to, yeah, let's maybe compare apples to apples here. Okay. Well, this is actually a little bit, so for just the completely unoptimized SOR, notice it's taking 7 seconds compared to the 0.06 seconds. Now that is in fact a big difference. It's a difference of about 100 times. But notice what happens if I change it to the optimized SOR3 method, which uses this compiled code here that really takes advantage of some sparse matrix computations. So if I do my SOR3, this is, I think, is going to be drastically lower. Okay, 0.8 seconds. Okay, now ours is still faster, but notice what's happening here. Our method is you know, roughly, not quite, but roughly, or a little bit more than 10 times as fast as this method. And a lot of this will change. So now we've got 0.07, and now it's 0.464. So if we do this a bunch of times, my experiments have been that we've gotten about, this method is about 10 times as fast as this method in terms of clock time. Now I also we're also getting like very we're getting a much smaller residual here. So I don't know if I change this to 4 if we get something different. Wow. The this really just shows that why a fine-tuned SOR method can work so well. In fact, I think if we do 1.99 here, now we have something. If I do a different value of W, now I have something that's even faster. Yeah, so now it's taking about the same amount of time. So we got 3301 iterations there. If I look at this, what are we going to get? 31,000. Wow. Okay, now this is 0.42. So we can see that this parameter really makes a big difference. Now, what can we say by way of comparison between these two methods, just the FOM and the SOR method? Well, definitely, if we look at this method, if we want the SOR method to run well, we need to be able to figure out, we need to know what 1.9 is, or we need to know what the optimal omega is. A lot of you in your graphs for your projects had that great curve graph like this, where you can see that the number of iterations gets smaller and smaller and smaller, and then it spikes up for W. Okay, so that spike is somewhat dramatic. If you're not near the optimal value of W, SOR isn't going to work well. So a lot of times with the PDE matrices, we can get a pretty good estimate for what W needs to be. Okay, but if we can't get a good estimate for what W needs to be, okay, then SOR doesn't really work, because I think, if I choose something like 1.4 here, it's all the way up to 5,000 iterations. It maxes out the number of iterations. Sorry, 50,000 iterations, and notice it hasn't even gotten anywhere. But I wonder what happens if I do 1.8. Okay, so 1.8 is okay, but again, we've maxed out our number of iterations. But here's the thing, though. For our FOM method, we're only building a subspace up to 375. If I just do 500 even, let's see what's going to happen here. 500, this here, if you think about this as being the number of iterations, this has 500 iterations. SOR has 50,000 iterations. So it's 100 times as many iterations. But notice that the algorithm only takes roughly 10 times longer to run. So the reason that it's like this is because the sweeps through the SOR method are very fast. You're just doing matrix vector multiplications. Whereas each step in the Arnoldi algorithm, you are orthogonalizing one vector, one big vector, with respect to a whole bunch of previous vectors, like 500. If we're doing 500, that's a big orthogonalization that we're having to do. And yes, you might also think part of the time is going to be that we're using a big, we're just using a regular dense solver here, but this is actually not that big of a deal in terms of time. So we can do time. We can measure this here. Time is equal. Tig is equal to time. Time, and down here talk is equal to time. So all of these, the reason I'm doing this is because all of these are the sorts of things that you might think about experimenting in your homework that you have to turn in, and stuff like that. And so now we can say time equals talk minus tick. And so what we're going to do, we're going to run this. We'll see that the overall time is going to be like 0.08, but that solve time is going to be like one order of magnitude below. So it's going to be like 0.001 or something like that. Okay. Oh, wow. That is surprising. Okay, here we go. The time is 0.004, 0.08. So, 0.0863 divided by 0.00415. Whoops. Yes. Okay. So it's 1/20th of the total time, is taken with that solve, and it's just one solve at the very end. So the solve is actually not the thing that's taking a lot of time for this, though that is certainly taking a non trivial amount of time. But the thing that's really taking a long amount of time here is just this orthogonalization that we do in every Arnoldi step. Okay, so now let's look at the GMRES. So GMRES, like I said, the good news is that GMRES is going to be very similar. We're just actually going to copy and paste our code. So it's going to do exactly the same thing. The setup is actually let me change this. The relative norm of the final residual. The relative norm of the final residual. This is going to be GMRES. Okay, now I'm just going to come down here. All right, I'm going to copy this. I haven't written I'm just doing this to make sure everything is working properly. Okay, right now the GMRES function is literally just the FOM function. I just want to do it this way to make sure everything is working fine. Okay, you know what? I also want to get rid of this time printout here. I don't care about that right now. Yes, okay. So I'm going to get rid of this. I'm going to get rid of this. And I'm going to come out here to FOM. Get rid of that. Get rid of that. Okay. Okay, so this is the GMRES cycle. So the only thing that's going to be different, literally the only thing that we're going to change is going to be this right here. And what we're going to do is going to solve the least squares problem. So it's going to be here instead of solve. We're going to put least squares. Yeah, okay. Let me change it in place. So least square, LST square. You can look up the documentation. Now remember for the GMRES method, what we end up solving is H bar is equal to beta E1. H bar equals beta E1. So it's not in FOM, it's H equals beta E1. In GMRES, it's the whole H bar matrix. So I need not to just go down to K, I need the whole thing. So this is the syntax. We've got, okay, y least squared. We're going to have the matrix. We're going to have the right-hand side. And then what we're going to do, we're going to tell it to use the LAPACK, or I think it's linear algebra pack. I don't know how you say it, if it's LAPACK or LAPACK. And this is what I was told to do. Okay. This is what the internet suggested. The best, which I think is probably ChatGPT suggested that this is going to be the best least square. So LAPACK, this is a Fortran linear algebra package. Okay, but now everything else is literally the same, except no, I think everything's the same. Yes, because the number of columns of H stays the same. I thought I might need to change that. Okay. Yes. Okay. Yes, I knew there was an issue there. All right. But I convinced myself there wasn't an issue. Oh no, this is right. I need the whole H bar matrix, but for the same reasons that I discussed, if we don't break down, K is equal to M, which is exactly what I want here. Okay. All right, so if we see what's happening here, we get about the same residual for FOM or GMRES. But notice that GMRES takes quite a bit longer. The real reason that it takes quite a bit longer is because solving the least squared problem takes a longer time to solve than just the regular problem. Sorry, the least squared problem takes longer to solve than the least squared problem takes longer than than the np.linalg.solve command does, or function does. Notice SOR is doing okay. It's not, we don't have quite as good. Now we're down to 10 to the minus 6 rather than 10 to the minus 9th. Still maxing out the number of iterations. And as we can see here, you know, it's still taking, what is that, 50 times as long, roughly, as this. Okay. All right. But, again, notice that we're doing 1/100th the number of iterations for FOM. But it's still, you know, it's not taking 100 times shorter. Okay, let's do this again. All right. So one thing that I do want to just look at, let's see what happens when we go to 64. Okay, now we can see that SOR is not scaling very well here. Oh, I need to, this is also not good, so we need to up this. So here, one of the reasons I'm doing this is to illustrate a problem that the method has in the way that we have coded it. The problem is that, like, what are we supposed to do if we're solving this in real life? Just keep increasing m over and over again until we get something that we need it to be? I mean, that's not really a practical way to do things. So what we need to do then is we need a way to sort of do this method until it converges. So we talked about this a little bit. There's a couple of ways that we can do this. The book mentions this problem. M really needs to be determined dynamically rather than something that's determined before you call the function. So let's see. I don't know how I can make SOR here converge. So notice sometimes FOM is faster, sometimes GMRES is faster. The good thing about GMRES is that with GMRES, you know for sure the residual of the next guess is going to be better than the residual of the current guess. So that's one of the reasons we like GMRES. It's also more stable than FOM. FOM really, in the case where we're assuming that the orthogonality space L is equal to K, for that to really work out well, we need our matrix to be symmetric. And if our matrix is symmetric, there's other stuff, there's better things that we can do. So for example, we're going to get to this, but if you think about if the matrix is symmetric, think about why this means that the H matrix has to be tridiagonal. And if we're in a tridiagonal matrix case, things are nice. And anyways, well, this is going to be what we talk about next week when we talk about conjugate gradient and stuff like that. I don't know why I'm running this again. I think SOR maxes out its iterations. 100,000. Okay, I'm just going to do this one more time. I'm not really sure why. So what I want to show you next, I'm going to make another function. It's just going to be called FOM cycle 2. And what we're going to do with FOM cycle 2 is that every 100, let's say, iterations, we're going to solve the system and see if it's in the tolerance that we want it to, be. And if it is, then we're going to return. If not, we're going to keep going. So everything that I've done up to this point, okay, is enough for the homework. And I've talked through kind of the way I analyze this. So I'm going to stop this video here, and then in the next video, I'm going to do a couple of different sort of bonus things that can show you how we can make some of these methods both converge faster and be a little more practical.